One problem that often is faced by PCB layout engineers is that they are often required to move signals across large boards where fast signals, where the signal starts at a reference plane that is properly at ground level, and then it crosses a moat, and then it goes into a region that is reference to power, and then it goes back to being referenced to ground, to another plane. And the problem is that when you switch a signal, this is a transmission line, let's say 50 ohms, is that you will have a current once this line switches up, right? And the current will be the voltage at the output of the driver divided by the source termination, right? R, and the characteristic impedance of the line, right? And if you look at the model of the transmission line, which we have here, is that once this voltage goes high and you see the impedance of the line, you have this current IL. But if you look at individual components of the line, the infinitesimal components, you'll see that this inductor will charge up and this capacitor will start charging, and the current will return through it, the charging current to the source, and which will be the power supply actually of this driver here, right? And it will keep once this is charged, then the next section, infinitesimal section, will charge up, and so forth and so forth and so forth and so forth until you reach the destination here, right? Where here, if it's a high impedance node, there will be a reflection, and it'll come back, and then this node will go back to full voltage V, and current will cease because the voltage here will be the same as here. But anyways, the problem is, well, this is traveling, right, where the edge is traveling, is that you have introduced cuts in the return path here and here, and this current doesn't want to go through, the bypass caps of the components that are maybe associated with this reference, this power plane, or the bulk capacitance of the DC to the converter is powering it. Instead, it really hugs the path of the signal, and what happens is this becomes because the current cannot flow anymore because you cut it out here. So this looks like a much higher impedance spot, right? So this whole section, and it'll ruin your waveform, as I will show experimentally. And so you have to find a way to keep this current returning in the proper following the line, right, in the path of least inductance, because the power plane is not perfect. It may have a very low inductance, but it still has inductance, and on top you go and cut it, so you essentially increase the inductance tremendously, right? And there is no way to properly return. So that is the statement of the problem. So I'll hang on, and we'll see the demonstration. This is our experimental setup. We have a pulse generator that drives a low impedance driver implemented with two packages of 74AC04, and impedance is around 1 ohm or so. The low impedance driver drives the 50 ohm source termination, and in turn that drives the input of the microstrip in the board, which is divided in two sections, where one section has a reference plane connected to ground, and the other one has a reference plane that is floating, but that it can be connected to ground through capacitors to provide a return path for the current, the high-speed current. And this is at different spots these are located, as you will see later. And this is to experiment to which is the best location to place these caps. And the output of the low impedance driver can be observed with channel 1 of the oscilloscope, and I'm using a FET probe so as not to load that spot. The spot between the source termination resistor and the first microstrip section is also observed with a FET probe into channel 2. And finally, the output of both microstrips the single microstrip rather, because it's divided in two sections really. It can be observed in channel 3, and that's it. This is the experimental setup. This is the low impedance driver implemented with 274 AC04 packages. Signal is fed to it from a pulse generator down this coax cable. Right at the output of the low impedance driver, this probe feeds or taps this signal to be displayed in input 1 of the oscilloscope, which is the yellow trace, and then follows at the output of the low impedance driver. There is a source termination resistor, 50 ohms, and there is a tap here for a probe that takes the signal into input 2 of the oscilloscope, which is the blue trace, and then right after the source termination resistor, the signal goes into the input of our test board, this board here, and the output of the test board goes into the into input 3 of the oscilloscope, and that signal is displayed as the magenta trace. Also, we have a display replicating the display of the oscilloscope, so we can see better with the camera, and that is the setup. We're now going to do 2 experiments to demonstrate the effect of black and or proper return current path for the microstrip in this board. Let me show you first how the board is made here. Let me show you. So the board at the bottom, it has a long microstrip, 20 nanoseconds long, and as you can see, is divided in 2 sections. The first section has a proper reference plane on top, on the bottom, or behind it in this case, and this is the input connector where the signal coming from the source termination comes in, and it goes and meanders, and it goes here, and here this other section does not have a grounded reference plane, rather is floating right now. It's unconnected, and it has a moat around it, which I will show you. I'll flip the board, and you can see through the light that there is a moat around that reference plane on top of that microstrip. I'll flip it again. And now to experiment with the board, as you can see, there is a number of surface mount capacitors around the moat, and there is one side of the capacitor actually connected to the reference plane, the floating reference plane, and the other side of the capacitor is connected to the switch, and the other side of the switch is connected to ground. So I can individually ground these capacitors with switches one by one if I wish, and see the effect that they have on the current path return. So in the strip line, and realize that the as you can see in the wave here, the switching times are really fast. Like at the input here, in this one here, I'm starting at 1 nanosecond, 1.5 nanoseconds, and because right now these switches are all open, the rise time has degraded, but it's still 11 nanoseconds, so it's pretty fast. So the current pretty much hugs the return path current. It hugs the microstrip, and where it finds too much inductance, like in this case where there is no proper return path, then the waveform suffers and is not what it should be. Let me now do the experiment 1, which is where I close these switches one by one. Let me make sure they show in the camera here, and I'll put the camera back a little bit, sorry for the in there, and then I start closing them, and you pay attention to the waveform on the screen there. So I start rather here, and there is some change, but at my age still pretty slow. As you can see, I'm at 9 nanoseconds right here, and I will keep switching them in and out, bling, bling. See, it's getting better. Getting better. There's not much effect in the middle, but as I approach again the edge here, then it gets better, got better, got better, got better, much better, and great. So now you can see that the edge is really fast. Now my edge is at about 3 nanoseconds, 2.7, 2.6 nanoseconds, sometimes 3. But this edge is much faster. So I started with 1.5 nanoseconds, and after 20 nanoseconds, which is a lot of trace of microstrip, I'm at about 3 nanoseconds. So I have added 1.5 nanoseconds of rise time, and this is for losses in the board. And you can see that at the input of the board, I can see the waveform that I should expect to see for a source terminated signal. So I can see I rise here, I go to half voltage because I'll have the 50 ohms of the source termination right here, and the 50 ohms of the first section of microstrip. So that's a divider, and so it's 2.5 volts here. And finally, when I get the reflection from the end of the open, I have an open, there's no termination here, open line at the end of the microstrip is open. So I get a reflection and I go all the way to 5 volts. And at the end of the line, of course, it behaves beautiful. It goes 0 and then it jumps all the way to 5 volts as it should be. And it's clean and nice. Also, it's interesting, I'm going to break it again. Okay, so I'm going to start opening. I'm going to do it the other way because it's more interesting. So I'll open it the other way. I open all the switches, and I want to point out that most of the switches are not necessarily end capacitors. Rather, what you need to provide, and I'll demonstrate it here, is, and I left one of them still is, that one, there. And I returned to original ugly waveform that I had. And what I want to demonstrate here is that you really don't need all these caps. Some people think, and I've seen this when I work on boards, that the capacitors that are sprinkled on power planes that are being used as reference as bypass caps for components are enough to provide a return path for current going in high-speed lines, and that is not so. But what you really need, and I'll fix it here, is just the ones where the line comes in, the signal comes into the line that is using a power plant. See, that got much better. And then where it exits. So you only need pretty much 2 caps next to the line. So they have to be close to the line, where, as I'll show you here. So the caps that I just turned on that fix it without having to deal with the other ones. And this is the section again that doesn't have a proper reference plane. Is here the signal comes in here, and there is this cap, and this cap right now is providing a return path for the current, the return current, a path for the return current, and also this other cap. So you need one where you enter the plane, and you need one where you exit the plane. The plane that is maybe a power plane, like I'm showing you here, a power plane, and I see that you see the mode, that plane, that is this plane right here. So you only need 2 capacitors. The rest, I mean, if they're great, you know, if you have more bypass caps. But you, strictly speaking, only you only need these 2. And the reason is because the current just hugs the microstrip. It won't take away, it won't go away from the microstrip, just follows the path of the microstrip from the input connector to the output connector. And so now what happens though, and I'll break it again, what happens, showing the screen here, demonstrate what happens when you have a clock signal. And I'm going to step the pulse generator to increase its frequency, and I'm going to go in steps of about 1 megahertz, all the way from 1 megahertz where I'm running right now, all the way to 50 megahertz. And you'll see the effect real soon here. I'm at 28, 29, and sometimes actually is nice, even though it's kind of broken. It just happens that a lot of factors just align the right way right now. I'm at 2 nanoseconds of rise time in the output. But as I go further, it just gets really ugly. And I'm at 45, 49, 50 megahertz right there. And you see that I have 8 nanoseconds of rise time, and the line looks horrible because there is not a proper return path for the current in the microstrip. But if I provide it, then that's what happens. It looks usable. I mean, that could use that receiver could use that. You see, it touches ground, very close to ground, and it goes to 5 volts, and the rise time is 2.5 nanoseconds. Of course, the period is 20 nanoseconds, so that would work. So if I step back, you'll see I'm gonna break it again, and I'm gonna send it back to one megahertz. Well, I'm at 1 megahertz right there, and I just want to show you what it looks like if it's nice. So all those transformations that the clock line have, and here you see that the shape does not change horrendously. The edges are there, and there is some change in the line. Then now we're back at 50, but there's not a lot of trouble with the line. There are some spots that are kind of weird, but for most the edges stay nice at around 2 nanoseconds, and they're usable. So that's I just want to point out, because I've seen cases where clocks in boards are horrendous because people have not taken care of the return path of the current in the boards for high-speed signals inside the boards, or on this, in this case, a microstrip. But I've seen it done in strip lines inside the boards, and the signal looks horrendous, just like this. So thank you for watching. So having seen the demonstration, we realized that then the solution to our problem is that along the current return path, what we have to do is that along the path of the transmission line, we have to put capacitors right under it if possible, so that the current return path can be reestablished, so the current can flow through from as it's flowing on the transmission line and it's charging these caps, right? It can, the current is going here, where it finds the break, it can go through the cap back into the path that it had before, and so forth. Here, when it finds the next break, it can, as it's flowing here, it can find a path to go, and it's right under the transmission line, so you put a cap there. And so that's why you bridge these gaps with capacitors, and that fixes the problem. That's what we have seen in our demonstration, and it worked rather well. Thank you. For my demo of current return path in high-speed boards, I laid out this board. It consists of a single microstrip that is 20 nanoseconds long, and it meanders through the whole board and is divided in two sectors. One sector, as a reference, has a solid reference plane behind it. I'll show you here. So this, the lower one has a solid reference plane, and the top side, the top section, which this one, has a reference plane that is not connected to the rest of the plane right here. So this one has a moat all around it, but it is possible to provide a path for the currents to return to the main plane by using these caps that are all around that cutout plane. And it's possible to by closing this switch, the switches that are in these pads here, and thus the current can move from here to through the cap to the ground and the plane. And I'll show you that there is a connection right here. You can see there's a via, there is a trace, and it goes to the capacitor and then to the switch and then to ground. So this is so that one can simulate the location of these return current path capacitors along the board and see what makes a difference, just as an empirical way of doing it. The schematic for the board is this. So it's, like I said, a single microstrip line, 50 ohm, and it's 20 nanoseconds long. And here are all the caps that are connected to that plane, that reference plane that is has a moat around it. And all the caps have switches, so all the caps are connected to the plane, and here, and they can be connected to the main plane, which is the ground ref, by closing the switches, and you can do one by one, and that is the board.